Hello, everyone, and welcome to our webcast titled Minimizing Water Discharge, Maximizing Reuse. I'm your host, Matt Grant, publisher of Power Magazine, and for today's program, we will hear from Bill Shaw, Senior Process Engineer for Veolia Water Technologies. Bill holds a BS in Chemical Engineering from Cornell University and an MS from the University of Wisconsin-Madison. He has 35 years experience in process design of evaporator and crystallizer systems. In the power generation industry, he's designed Zero Liquid Discharge systems for wastewater from cooling towers, FGD scrubbers, and gray water from coal and petcoke gasification plants. He's also published articles in journals such as Power, Chemical Engineering, Water World, and Ultra Pure Water. This presentation today will last about 45 minutes, and we'll follow up at the end with a Q&A portion. Before we get started, I'd like to point out a few housekeeping items. At the left of your screen, there is an area where you can type and submit questions to the speaker. So feel free to send in questions at any time during this presentation. We definitely strongly encourage that. We'll try to answer as many as we can towards the end of the program in the Q&A session. If you are experiencing any technical difficulties, you can also type that problem in the same area at the left of your screen, and our production staff will assist you right away. This program is available for download, and you can actually access a PDF of the slides under Event Resources at any time via this live studio link. This webinar will also be archived on our server, and future viewing will remain free of charge. So you can use the same URL to reach the archive program as you did to reach the live program. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. Before we begin, we would like to very much thank Veolia Water Technologies for underwriting today's program. Their great generosity allows everyone to attend this presentation at absolutely no cost. So with that, I will turn the program over to our speaker, Bill. Bill, take it away.
Well, thank you, Matt, and welcome everyone to the webcast. Thanks for spending some time this afternoon to learn about Zero Liquid Discharge and some of the technologies involved in achieving that goal. As Matt said, I'm a Senior Process Engineer with Veolia Water Technologies. My name is Bill Shaw, and I'll be presenting this webcast sponsored by Veolia. Veolia is the world's largest environmental company with over $26 billion in revenue and 160,000 plus employees worldwide. Veolia is focused on three areas: water, waste, and energy. Veolia supplies drinking water and wastewater treatment to millions of people and companies worldwide. Veolia provides collection and treatment of solid waste through municipal and industrial customers. And Veolia also provides heating and cooling networks in thousands of cities and industrial sites. I represent Veolia Water Technologies, a business unit of the main Veolia company, and we provide technologies, products, and design, build, and operate services to municipal and industrial clients. In the power generation industry, Veolia Water Technologies provides water technologies and services that you can see listed here, basically throughout the power plant. Now that we've had that little commercial introduction, let's get into the overview of the various technologies that are applicable to zero liquid discharge and water reuse mandates that are being imposed in many industries, the power industry in particular. Here's a brief overview of the topics that we will cover in this presentation. In particular, I want to present a new process to treat FGD wastewater called the cold process, which promises major savings in operating costs. But we're going to start with the basics, look at some applications, and then look at the economics of the approaches that we talk about for zero liquid discharge. These are the typical unit operations which might be required to achieve zero liquid discharge. These are basically the tools we have to achieve wastewater volume reduction and zero liquid discharge. Some of these are familiar to you, others may be new, and we're going to talk about the ones in detail that are highlighted in red, because that's all I know about really is thermal processes, and so that's what I'm going to share with you today is some insights in how we can use thermal techniques and thermal methods to reduce and eliminate wastewater discharges. This is the basic flow sheet for any zero liquid discharge. It may involve some or all of the steps that are shown on this flow sheet, but this pretty much covers what's involved. Typically, wastewater has some sort of pre-treatment that depends on what's in the water, followed by a concentration step to reduce the volume of the wastewater, followed by a solidification step to separate out the solids dissolved in the water, and usually those get disposed of in a landfill. As I said, the dissolved salts are separated from the wastewater. The water is usually recovered and reused, perhaps after some post-treatment, if its quality is not suitable for the purposes for which we want to reuse the water. So we're going to take a look at each of these steps in detail and talk about what's involved in each one. First of all, pre-treatment. These are some of the typical unit operations which might be required to pre-treat wastewater prior to concentration. The water may contain suspended solids, oil, grease, biological material, all of which could foul and plug the evaporator, crystallizer, reverse osmosis, whatever concentration devices we're planning to use. Sometimes scaling components are present in the water, and we want to eliminate them or reduce their ability to deposit in the concentration devices that we use. So these are all some methods which might be used as pre-treatment. We're not going to cover any of these in great detail, but just be aware that these may be part of a zero liquid discharge scheme. The two most common methods of concentrating wastewater are reverse osmosis and evaporation. And again, I'm not going to spend the time to talk about reverse osmosis, because I'm not an expert on that, so you'll have to get that expertise elsewhere. But I am going to talk quite a bit about evaporation, which is often used in thermal ZLD systems. Reverse osmosis will get you some concentration, and this is an important thing to know, that each of these concentration methods, reverse osmosis and evaporation, have an upper limit in how high generally you can concentrate a wastewater. For RO, you can get up to 6 to 8% by weight of dissolved solids in the wastewater. So whatever your starting point is, you can get to 60 to 80,000 milligrams per liter of TDS, which is 6 to 8 weight percent. If you get above that, reverse osmosis kind of doesn't work so well anymore because you're getting above some osmotic pressure limits in the RO system. RO is generally the lowest cost option for concentrating wastewater, but the RO membranes are susceptible to scaling and fouling, so you have to be very careful about pre-treatment before you put wastewater through an RO system. As far as evaporators are concerned, they're able to get a much higher concentration level, up to 20 to 25% by weight total dissolved solids. Above that, you're getting into an area where salts start to crystallize out. And unfortunately, a falling film evaporator can't handle the crystallization of solids. It can handle only evaporation. So we have to stay below that 20 to 25% limit of TDS. Because an evaporator is made out of high alloy materials, it does have, and because of phase changes involved, we have higher capital and operating costs than a membrane concentrator, but we can get to higher concentrations. So that's kind of the reason for being as far as evaporators are concerned. We can't get to dry solids in an evaporator. We can only concentrate up to 20 to 25%. We do get the water is recovered, and it's usually a very good quality water, so it's good for a lot of reuse purposes. The solidification step in a ZLD scheme is one of basically three ways you can do that. One is to use crystallization with dewatering, and that's what we're going to talk about in this particular presentation. But don't forget that when the conditions are suitable, evaporation ponds and spray dryers can be used to also achieve solidification. The kicker on those is that for an evaporation pond, obviously, you've got to have be in an area with good solar energy and lots of empty land. As far as spray dryers are concerned, you need waste heat. So those conditions aren't present always. So let's talk about crystallization. In general, the type of crystallizer that's used for zero liquid discharge wastewater treatment is a forced circulation type crystallizer, and we'll talk about what that means in a little bit. The crystallizer has even higher capital and operating costs than the evaporator does, but you are able to get a solid product which can be, in most cases, put into a landfill to dispose of the solids. And we also get to recover the water, which is generally, again, a very good quality water, so it can be reused. The solid separation is done by either using a centrifuge or a pressure filter, and I'll talk a little bit more about those as we go through the presentation. It is possible, a lot of people ask this, can you get pure salts? Can you purify salts and recover the salts and reuse them? And yes, that's possible, but generally some additional steps have to be put into the process in order to get to a pure salt. So that's a little more tricky. And we aren't going to get into it here, but it can certainly be done. Spray dryers, I'm not going to talk about spray dryers very much, but spray dryers are another thermal method of achieving solidification in a ZLD scheme. The problem with spray dryers is that unless the heat waste heat is free or very low cost, spray dryers are quite inefficient. They take about, it takes about 1,000 BTUs to drive off a pound of water in a evaporator, but it takes almost twice or 2.5 times that in a spray dryer, just because the spray dryers are very inefficient in terms of the heat transfer. So unless that energy is free or very, very low cost, spray dryers are usually not very economic. Also, you don't get the water back. It basically gets vented to the atmosphere. So, and finally, when we are looking at the recovered water, whether we use evaporators or crystallizers or RO for that matter, when we recover the water in our ZLD scheme, it may have some things in it that we don't want, especially if we're going to reuse the water. So sometimes we have to do some additional treatment on the recovered water itself, especially if you have volatile components which could wind up in that recovered water. Things like volatile organic compounds or ammonia or volatile solids like boric acid. Those things tend to wind up in the recovered water. And if the downstream process where the water is going to be reused can stand that, it's fine, but otherwise you're going to have to do some things to remove any impurities, depending again on what purpose you're going to reuse the water for. So these are some of the things that might be involved in post-treating the recovered water. So let's talk about what sorts of things we have to, now that we know what unit operations are involved, let's talk about some of the things that we have to consider in designing these processes. And in particular, we're going to be concerned with things like scaling and fouling in any kind of a thermal system, or an RO system for that matter as well. And this is the deposit of low solubility salts on the membrane surfaces or on the heat transfer surfaces, which impede the thermal process or the osmotic process in an RO system. So scaling and fouling are certainly things that we're concerned about. As I mentioned, the recovered water, the distillate or the permeate, we sometimes have to be concerned with the carryover or the volatilization of things like organic compounds or boric acid that could wind up in that recovered water and may have to be removed. Things like highly soluble salts, the presence of highly soluble salts that don't really want to come out of solution, those tend to kind of impede the separation process of getting the dissolved solids from the water because they increase the osmotic pressure in an RO system and they increase the boiling point elevation in a thermal system. So those two, those salts, and those are typically chloride salts, highly soluble chloride salts like calcium chloride, magnesium chloride, ammonium chloride, or nitrate salts, or salts of organic acid, acetates and formates. Those salts tend to not want to come out of solution. They tend to build up and they tend to increase the resistance to heat transfer or osmosis in the concentration systems that we use in ZLD. The other things we need to worry about are foaming. Foaming is often caused by dissolved organic material or suspended fine matter. That's a problem. And finally, those organics and suspended solids, and when the brine becomes highly viscous, it becomes really hard to do the solid separation, to separate out any crystals that we make from the mother liquor to solidify those crystals for disposal. So all of these are things that we have to look at the analysis of the wastewater, and those will cause us concern, and those will adapt the process that we choose for zero liquid discharge. So let's talk about some specifics here now that we've covered some general topics. And in particular, let's just talk about power plants and the use of evaporators and crystallizers in power plants. It's not a new thing. Since the 70s, evaporators and crystallizers have been used for concentration and elimination of cooling tower blowdown in power plants, especially in the West, especially power plants along the Columbia or the Colorado River. Cooling tower blowdown is generally hard. There's the hardness is involved in the water. There's silica in the water. It's generally not too high in TDS because the cooling tower has limits on how high you can concentrate to without getting into problems with drift and also with scaling in the cooling loop in the power plant. The typical zero liquid discharge system that's evolved over the years for cooling tower blowdown usually involves almost all of the steps shown here. Side stream softening to get rid of some of that hardness, some of the calcium and magnesium that causes scaling. Then a reverse osmosis step because the TDS isn't too high, so we can get some concentration in an RO system, followed by an evaporator, which is typically a MVR. MVR stands for mechanical vapor recompression, and we'll talk what that is in a minute. But it's basically a compression-driven or electric power-driven evaporator rather than a steam-driven evaporator. And it's sometimes called a brine concentrator. That's another term you'll see used. And that evaporator can concentrate, as we said in the earlier part of the presentation, up to 20 to 25%. And then that 20 to 25% brine that comes out of the evaporator goes to a forced circulation crystallizer, which may also be an MVR-driven or a steam-driven type unit. And then finally, the final solid separation is done a lot of times with what's called an Oberlin filter. It's again, I'll talk later about what that is specifically, but it's an automatic indexing pressure filter, or sometimes the centrifuge is used to separate out the solids. This is a typical brine concentrator system in all its required components. Basically, if you start over on the right, you'll see the feed stream goes into a tank, and in the tank, some acid is added, and that's to convert any alkalinity that's in the feed to CO2. That feed then is preheated by exchanging heat with the outgoing distillate or recovered water in a plate-type heat exchanger, which is called the feed preheater. And then the feed goes up to a deaerator. And the deaerator is where the CO2 that was created in the feed tank is stripped out along with any dissolved oxygen. And that's to keep the evaporator, which is the next piece of equipment, from corroding by taking those oxidizing atmospheres out of there. The actual evaporation occurs in a falling film evaporator, which is driven by a mechanical compressor, which pressurizes the water vapor and raises its temperature. When you pressurize a vapor, when you pressurize water vapor, you raise its temperature. And so that hotter water vapor can be used instead of external steam as the heat source for the evaporator. So in essence, the MVR, or mechanical vapor type compression system, is really an open cycle heat pump. We're taking low pressure water vapor and pressurizing it so we can use the heat to do the evaporation. So we recover all the latent heat of vaporization this way and reuse it. So it's very energy efficient. When the brine has been concentrated in the falling film evaporator, we have a seed recycle system, and we'll talk about seeding in a minute also. But basically, the seed recycle system takes the seeds out of the evaporator blowdown and sends them back into the evaporator, and the blowdown itself then goes to the next step in the process, which would be a crystallizer. So here's a picture of a brine concentrator. This one's about a 250 gallon per minute unit. It's about 15 foot in diameter, and it stands about 100 feet tall. And you can see some of the components in this picture. It's a little hard to see the other ones, but the deaerator you can definitely see, which is sort of hanging off the side to the left. There's a feed tank, which is sitting in front of the unit, and then the compressor sits in that little shed in the front, which is basically a sound enclosure to keep the noise down. But that's a typical falling film evaporator. This is a cutaway of that evaporator, and you can see that what's inside the unit is a big central pipe, and there's a pump that's connected to that pipe, and it basically pumps the brine around a circuit from the bottom of the evaporator up through the middle to a distributor assembly at the top. And I'll show you a close-up of that distributor assembly in a minute. But the brine then is distributed down a vertical tube bundle where it's heated and evaporation occurs. And in the bottom is what we call the vapor body, that fatter section that's sitting there. There is a level of liquid in that vapor body that provides submergence for the recirculation pump. And then the vapor separates out from the liquid in that body and goes out through the side, you can see, off to the compressor suction. So that's sort of what's inside the evaporator. If you look a little more closely at the top, you can see that this brine distribution device, you see the central recirculation pipe coming up through the middle, and the brine flows up through that pipe and spreads out on that top perforated plate, and then you can see some overflow weirs, and there's a second plate underneath. And basically those two plates distribute the recirculating brine evenly across the whole cross-section of the evaporator and around the inner circumference of each tube. Again, there's a tube bundle. We've taken the tubes out of the picture here to make it clear, but there's a whole tube bundle in there. At the bottom of the evaporator, you could see the purple tube sheet at the bottom. Again, we've taken the tubes out for the purposes of seeing what's in there. You see that central recirc pipe. And at the bottom, we have the brine flowing from the bottom tube sheet, collecting in that conical section where it maintains a level in that unit, and that level is maintained to provide some submergence again for the recirculation pump. There's mist eliminators that go around the top of that vapor body, and the vapor has to pass through those mist eliminators, and they basically scrub out any droplets of water that might be carried along with the water vapor. And so a dry vapor exits at the vapor outlet. So on the individual tubes, this will give you a little idea of what's going on the tube surface itself. You can see at the very top is the distribution plate, and that brine falls through the holes in the perforated distribution plate onto the top tube sheet. And so there's a level of liquid, it's a fairly thin level of liquid that sits on the top tube sheet. And that brine then flows down the inside wall of the tube around the entire circumference. And out on the outside of the tube, vapor, which came from the compressor, condenses on the outside of the tube and gives up its latent heat, which transfers across the tube wall and causes the film on the inside of the tube to boil. And the vapor flows in the same direction down the tube along with the liquid to the bottom of the tube, and at that bottom vapor body, that's where the separation of the vapor and liquid take place. Now you'll see some little dots suspended in the brine. Those are meant to represent seed crystals. And seed crystals are basically little crystals of calcium sulfate that are distributed throughout the brine that's circulating in the evaporator. And why are these little seed crystals in there? They're there because they provide a place for any low solubility salts which want to come out of solution, like calcium sulfate, calcium carbonate, calcium phosphate, silica. Any of those low solubility calcium salts are going to precipitate out fairly quickly in the evaporator, but instead of precipitating on the heat transfer surface of the scale, they precipitate preferentially on the seed crystals, and the seed crystals grow larger. So those seeds are really there to keep the evaporator tube from scaling. The question might occur to you, well, how do the seeds get in there in the first place? And they're deliberately placed in a seed tank, which you see here, which is connected to the evaporator. And initially, when we start the system up, we actually put calcium sulfate into the seed tank and mix it up with water and pump it into the evaporator so that the system has a bunch of seed crystals in it when we first start it up. And then we have a hydrocyclone, so when we pump the concentrated brine out of the evaporator, we can spin those seed crystals back in the hydrocyclone, put them back in the seed tank and pump them back into the evaporator. So we don't lose all of the seed crystals out the back end of the system. So this is kind of what we call a seeded slurry process. And this evaporator is technically correctly known as what we call a brine concentrator, is a seeded slurry falling film MVR evaporator. So there's a mouthful for you. Seeded slurry MVR falling film evaporator. But anyways, the whole idea is to keep the evaporator tubes from scaling with low solubility salts by using this seeding technique. Okay, so let's take a look at the the crystallizer, which is the next step or the next technique that we talked about for in our ZLD scheme. And these are two examples of how a forced circulation evaporator or crystallizer can be configured. And it can be either configured with the heater being vertical or the heater being horizontal. It really doesn't make a difference. The important thing in a forced circulation evaporator is that the heat exchanger is located below the level of liquid in the crystallizer vapor body. There's a level that's maintained in that vapor body. The crystallizer heater is submerged under that level. So the crystallizer heater body is flooded, and no evaporation occurs in that heater. All that happens is sensible heat is transferred. The evaporation occurs when the heated brine exits the heat exchanger and it flash boils when it enters the vapor body. So it's a flashing type evaporator, not a film type. And this is important because that vapor body, that flashing action at the inlet to the vapor body causes the brine to become supersaturated, and that means that it's holding more solids than it can, so crystallization starts to occur. And the idea is that vapor body, that volume of liquid in the vapor body is sufficient, has a sufficient residence time to relieve all of the supersaturation and grow the crystals in the tank. So by the time the brine comes back to the heater, all of the supersaturation has been relieved. So we don't get crystallization occurring in the heater itself, because that could result in the crystals adhering to the heat transfer surface. So this is a typical forced circulation type evaporator. Here's the whole system along with the dewatering, and you can see that and this is an MVR type brine crystallizer. So again, we're using a compression device, a compressor, to compress the water vapor, which heats it up so we don't have to use external steam to drive the crystallization process. You can see a dewatering device is used, which separates out the solids that are produced in the vapor body, and those solids then go to disposal. The mother liquor is sent back to the crystallizer. You can also drive the crystallizer with steam, external steam. Looks like my diagram fell apart here, but so forgive the facts that the pipes aren't quite connected. But external steam can be used to heat the crystal heater. And instead of using a compressor, we have a condenser that's cooled by cooling water to take the evaporated water and condense that. This is a picture of a forced circulation crystallizer. Again, the main thing to note is that heater is sitting well below the level of the liquid that sits up in that crystallizer tank, so that the heat exchanger is flooded and no boiling occurs and no crystal growth occurs in that heater. It all goes on in the vapor body. Here's, again, we talked about some of the different ways to separate solids out that are crystallized out in a crystallizer. The first one is the Oberlin belt pressure filter. Then we have centrifuges. And if you don't like mechanical ways of separating out the solids, you can stick a spray dryer on the back end of a crystallizer and dry the slurry of crystals and mother liquor. But typically, either the pressure filter or the centrifuge are used to separate out the solids. Here's a picture of a whole power plant with the ZLD system. You can see, again, the four main steps. Pre-treatment over on the right-hand side. This particular plant is doing side stream softening of cooling tower blowdown. This is the Harquahala station in Arizona. You see an RO system over on the right-hand side in a building. Then we have two evaporators and two crystallizers and two solids dewatering devices. So this system has been divided up into two parallel trains of evaporator, crystallizer, and solids dewatering. This system, by the way, is about 200 gallons a minute of water that's treated in this wastewater. So each evaporator does about 100 gallons a minute. This is another larger plant which is treating about 3,000 gallons per day, or 3,000 gallons per minute of mine wastewater from a coal mine. Again, you see the pre-treatment off to the in the foreground, a big building which houses lots and lots of reverse osmosis skids, and then outside on the right-hand side, an evaporator and a crystallizer and solids dewatering inside a building. So this is a bigger ZLD system, but again, the same four steps: pre-treatment, evaporation, RO, evaporation, crystallization, and dewatering. We talked about cooling tower blowdown in power plants. The other big item which we want to talk about is FGD scrubber blowdown. These are not very common. There's only a few of these in the world. Most of them are in Europe and China, and there's only one or two here in the U.S. Again, the idea is to take FGD purge water and eliminate the discharge completely. So here's a plant in Italy that does that, a coal-fired plant. The thing to understand about FGD purge is that it's very, very different from cooling tower blowdown. It's a lot more concentrated. It's got a lot more chloride, so it's very corrosive. It's got a different set of cations. It's mostly calcium and magnesium base as opposed to sodium base for cooling tower blowdown. Lots of suspended solids in it. It's got gypsum. It's saturated in gypsum because that's the byproduct that's made in the scrubber. And it's also got a lot of other things in it, like heavy metals, boron, silica, selenium, dibasic acid, sometimes COD, who knows. There's a lot of different things that can be involved in FGD purge water. So what does that mean as far as ZLD is concerned? Well, because the TDS is high, usually you can't use RO. And that's also because of the high suspended solids as well. But generally, RO is not a good candidate to treat FGD wastewater unless you do lots and lots of pre-treatment. So it's generally not used. Chlorides are so high that you really have to be concerned about the materials of construction and the pitting and stress cracking that occur because of high chloride concentration. So we get into some very noble materials of construction. Likewise, the salts, the predominant salts in FGD purge are calcium and magnesium chlorides, which are acid salts. The pH is not neutral. It's in the acid range. So again, that gets you into that whole corrosion concern with FGD. So what do we use? What do we have to deal with when we're dealing with FGD? Well, typically on the evaporator, we're looking at a minimum of a super duplex 2507 type stainless steel or a super austenitic stainless steel like AL6XN or 254 SMO. Tubes are generally titanium, pure titanium, for their corrosion resistance because the tubes are the thinnest part of the evaporator. So grade 2 pure titanium is often used for the tubes. And the crystallizer, because the concentrations of chlorides are even higher, we get into the Inconels, the Hastelloys, those high nickel, chromium, moly alloys that are pretty resistant to pitting and stress cracking corrosion. But they even are susceptible to it, so you have to be careful in looking at how low the pH goes. So that's definitely a concern. And then tubes, we still use titanium, but we add palladium to alloy with the titanium to make it even more corrosion resistant. So that's the grade 12 and grade 16 titaniums. Those are typically used for tubes. So for FGD, we tend to have a different flow scheme or ZLD scheme than we do for cooling tower blowdown. There's really two alternatives. One is to just take the calcium and the magnesium out of the FGD purge water. It causes so many problems in the evaporator and crystallizer that it's easier to just remove them up front and replace the calcium and magnesium with sodium. That's basically what lime soda ash softening is. You use lime to precipitate out the magnesium and soda ash to precipitate out the calcium, and you're left with basically a sodium chloride solution. And that's pretty easy to crystallize out in a conventional crystallizer. Or if we don't want to soften, because softening requires the use of lime and soda ash and it produces a lot of sludge, there's another set of techniques that we can use, which is to use a regular falling film evaporator and then either take the brine and dispose of it somehow from the evaporator, not crystallize it at all, or use what we call a cold crystallizer. And that's the new technique I want to talk to you about that has some very interesting economic implications for FGD wastewater. But let's look at these alternatives first. The first one, as I said, is to soften the FGD wastewater using lime and soda ash. Lime precipitates out the magnesium as magnesium hydroxide. Soda ash precipitates out the calcium as calcium carbonate. Those are removed as sludge from the softener system. And then the brine, which is left, is basically a sodium chloride solution, and that goes to a conventional evaporator and crystallizer. So we have a lot of chemicals required to do this scheme, and we also have a lot of sludge that we have to dispose of. Brine disposal is done really with three different methods. One is to concentrate the brine or the FGD purge in an evaporator as far as we can go, reduce the volume as much as we can, and then send that brine to either, number one, an evaporation pond, if you can build an evaporation pond, or two, mix the brine with some sort of cementitious material like fly ash or Portland cement or gypsum and dispose of the brine as a paste or a solid in a landfill. Or three, use that notoriously inefficient spray dryer, but if you have a cheap source of low-grade heat, that might be a good way to do it. So those are some other ways that we can get to zero liquid discharge with FGD. And finally, we have this cold crystallization process, which the name kind of tells you something about what it's all about. It's a low temperature process, and it requires little or no chemical pretreatment, and I'll explain why in a minute, and it produces the minimum amount of solids to dispose of. So unlike the softening approach, we don't need a bunch of chemicals to pretreat and the equipment to pretreat the FGD brine. And also, unlike the softening system, we don't have a lot of sludge that we have to dispose of. So how does this cold process work? Well, first of all, what does cold mean? Well, again, it's a low temperature crystallization process. It's actually an acronym. It means crystallization of high solubility salts at low temperature and deep vacuum. So this kind of tells you where cold crystallization applies. It applies when you have highly soluble salts like calcium chloride and magnesium chloride, which happen to be the predominant salts in FGD wastewater, and it operates at low temperature, and the low temperature is generated by operating the system in a deep vacuum. Okay? So that's what cold means. Well, again, so what? This phase diagram for calcium chloride might help to explain what's going on. There's two lines on this diagram. First of all, it's on the vertical axis, we're looking at temperature. On the horizontal axis, we're looking at the weight percent of calcium chloride solution in water. And you can see a red line that's drawn on the chart, which is the boiling point curve for calcium chloride. So if you follow that red line and you look at any concentration of calcium chloride, you can look over on the left and or the right, and you can see the temperature at which that solution will boil at. And you can see that in the boiling temperature, when you get up into high concentrations of calcium chloride, you can see that those temperatures get really, really high. We're talking, 170 degrees Celsius or 300 and some degrees Fahrenheit to boil a 70% solution of calcium chloride. So it gets very hot. You need a lot of energy to get that calcium chloride out of solution. The black line represents the solubility of calcium chloride, and you can see it's got all kinds of inflections in it, and those are where different hydrated salts of calcium chloride form at different temperatures. The point is, where the two curves meet is where the crystallization occurs. Where the boiling point red line meets the black line is where the crystallization can occur. And you can see on this chart they don't even meet. So we have to keep going even further in concentration to get the calcium chloride to come out of solution. It's really, really hard to get the stuff to crystallize out. But if you can reduce everything in terms of the pressure, if you can draw the system into a deep vacuum, all of a sudden what happens is that boiling point curve drops, because under a deep vacuum, the boiling temperature of water or any solution that's based on water becomes lower. And you can see that now the red line and the black line intersect, and this is at a pressure which is quite low. It's about 0.5 psia. But you can see that if I can get that low pressure, I can get calcium chloride to precipitate at a concentration of roughly 60% at a temperature of 176 degrees Fahrenheit. So by lowering the pressure, I lower the temperature, and I can get the calcium chloride to actually crystallize out at a much lower concentration. So that's the whole idea of a cold crystallizer, is to lower the temperature and bring the system under a deep vacuum. So here's our conventional crystallizer. Again, on my slide, it seems like it all got disjointed here somehow, but that crystallizer is what we've seen before, steam-driven crystallizer with a condenser. The only difference between the conventional crystallizer and the cold crystallizer is the addition of a pretty good vacuum system to draw this system down into a deep vacuum, and then we have to use chilled water to get the vapor to condense. So this is our cold crystallizer, and all of that boils down to this economic comparison. If you take a look at two different ZLD systems, both sized for 350 gallons a minute, one being using softening plus evaporator plus a crystallizer to achieve ZLD for FGD. The second system, same capacity, using just an evaporator and a cold crystallizer, no softening. You can see that capital costs are roughly the same. Operating and maintenance costs are roughly the same. But when you get into the operating cost, the cost of the chemicals, that softening system requires a lot of chemicals, and it requires a lot of sludge disposal costs, which we don't have for the cold system. We still have some chemical costs, mostly for caustic and acid for pH control, but it's very low. And we do have some disposal costs because we're going to crystallize out the salts and put them in a landfill, but we don't have all this extra sludge that we have from a softener. So when you get to the bottom line, you can see that the cost per gallon of to use the softening system is much less than or to use a cold system than when you soften completely. So that's the big advantage of this cold crystallizer system for FGD ZLD applications. So again, this is a summary of the cold process. It's just a deep vacuum forced circulation crystallizer driven with steam. You won't be able to use MVR on a cold crystallizer, but we have the low operating temperature, which lowers the solubility and forces the salts out of solution at low temperature, getting them to crystallize out. I think that's I probably have used up all my time here. This is my contact information if you have any questions. We will take questions from the audience as long as we have some additional time here. And I thank you very much for your attention. There's another slide here which gives you some more information to give you some additional resources on these topics. So thank you all very much for your attention. I hope that you learned something useful here, and be happy to take your questions as we have time. Thank you.
Yeah, thank you very much for the great presentation, Bill. We've had a number of really good questions come in. We've got a few minutes here before we wrap. I know we've had some questions on the slides, and just a reminder that this program is available for download, so you can access a PDF of all the slides under the Event Resources tab via this live studio link at any time. So I encourage everyone to definitely continue asking questions. We'll get to a few here as time allows, and we'll definitely follow up with all others individually following the program via email. So to get things started here with a few questions for you, Bill, First one is, we are not sure what process to pick. Does Veolia have the capability to sit down and give us options between membrane, thermal, or a combination?
Absolutely, and that's the value that we try to present to you, is to help you not only by just selling you equipment. We're a resource to do the process design and figure out how to optimize it and do it for the lowest capital and operating cost possible. So that's a big service that we supply, and that I think we have proven to our customers that it's a very valuable service. Great.
Next question for you here. What is the typical TOC reduction of the distillate from an evaporator and crystallizer?
Well, TOC is a tough one. Usually if you have organic compounds in the feed water, you're going to get some fraction of them to wind up in the distillate water. So it's just a matter of what organic compounds are in there, how volatile they are, how their volatility compares with that of water. But typically, if you have organics in the feed, you'll probably see some organics in the distillate as well. So it's a matter of how much you can stand in your reuse processes.
Great. Next one for you, Bill. Will a continuous centrifuge be as economical as a pressure filter batch, and how effective are centrifuges in these applications?
Excuse me. Centrifuges are used generally when you have higher capacities, higher solids production rates. It's really a 6 of one, half a dozen of another. In comparable size ranges, the the pressure filter and the centrifuge are pretty close in cost and price.
Okay, great. And last question for you here. As I mentioned, for everyone in the audience, please do feel free to type in your questions. And like I said, we'll get to all others following the program. But last question, and then we'll wrap. What is the normal life expectancy of the tube bundle and the seated film MVR falling film evaporator?
Tube bundles and the system itself has a typical life of 30 years. Now, will all of the tubes last 30 years? Probably not. You're probably going to wind up over the years plugging some tubes because they've developed a leak. But in general, those tube bundles are designed to last for a long, long time. And that's really important. You know, I talked about using titanium for heat transfer surface, and that's a really good metal to use because titanium forms an almost impervious oxide coating that prevents it from corroding. But there are some things that get through that, and in particular fluorides, the element F. So when fluorides are present, then you need to look at alternate materials even for the tubes. But we try to do, we do corrosion testing, we do all sorts of things to try to pick the most robust and long-lived materials we can for the heat transfer surfaces. And you know, in general, you can expect a lifetime of 30 years for that tube bundle.
Okay, great. Well, we have officially reached the end of the program, so as I mentioned before, we will definitely follow up and address further questions individually by email. Thank you very much once again to Veolia Water Technologies for underwriting today's event. Thank you all in the audience for attending. Thank you, Bill, for the great presentation. We hope everyone in the audience will benefit from today's program. Hope you all have a great day.